Okay, let's dive into this. Welcome to today's Explainer, where we are embarking on a massive, centuries-long cosmic detective story. For the longest time, humanity has just looked up at the night sky and wondered exactly where we fit into the grand design of the universe. So today, we're going to break down the absolutely fascinating journey of how we figured out our true place in the sprawling Milky Way. It's an incredible tale of brilliant minds, out-of-the-box thinking, and some seriously perspective-shifting breakthroughs.
To really appreciate the scale of this whole scientific achievement, we gotta ask ourselves a pretty tough question. How do you map a forest when you can't actually leave the woods? This hits the nail on the head for our central problem. We are literally trapped inside the Milky Way galaxy. We can't just step outside, whip out a camera, and snap a picture of the whole thing. Instead, we have to figure out the shape of our home from the inside out, using only the clues we can spot from our one specific, totally isolated vantage point.
Now, for centuries, we made a seriously flawed historical assumption. We assumed Earth was the center of a spherical universe, with the sun and stars just circling us in perfect harmony. It was, well, a natural, highly egocentric tendency to put ourselves right in the middle of everything, right? But the visual reality of the night sky totally challenged that. When we look up, we see this faint, band-like ribbon of stars. Think about it. If our galaxy was a giant sphere, we'd see stars scattered evenly in literally every direction. But that flattened, band-like visual reality, it strongly suggested we actually inhabit a flattened disk, and we're sitting right inside its plane.
So you might be wondering, why not just send a probe up and out of this flattened disk to get a better look? Well, let's look at this absolutely mind-bending number, 0.02. That's 0.02 light-years. Voyager 1 is humanity's most distant human-made object. It's been soaring through space for nearly half a century, and in all that time, the whole shebang, it has only covered a distance of 0.02 light-years. To actually fly out of the galactic plane and see its shape, we need to travel hundreds, maybe thousands of light-years straight up. So yeah, physically leaving simply isn't an option. We had to use our minds instead.
And that brings us to the timeline of our cosmic detective story. We're going to start in the 18th century with William Herschel's map, then jump to 1908 with Henrietta Swan Leavitt's standard candles, move into the 1920s with Hubble and Shapley, and finally arrive right at the modern era with the 2013 Gaia mission. Chapter 1, The First Galactic Map. William Herschel's 18th century blueprint. Our very first detective is William Herschel. Now, what's really interesting about this is that Herschel, who you might know for discovering Uranus, wasn't just an astronomer, he was a bold mapmaker of the cosmos. Armed with a handmade telescope that let him peer way deeper into the dark than anyone before him, he and his sister Caroline took on a task of just sheer, tedious patience. They divided the night sky into about 600 specific zones and literally counted stars on a grid night after night. All this incredible manual labor led to a massive breakthrough. He actually confirmed that our galaxy was a disk-shaped structure. But there was a catch. He incorrectly placed our solar system right near the center of this disk.
So why was he wrong? Well, it all comes down to a massive missing clue: interstellar dust. Herschel had absolutely no idea that giant clouds of cosmic dust were completely blocking our view of the stars in the Milky Way's central region. Because this dust essentially hid the true, incredibly dense heart of the galaxy from him, he just assumed the star distribution was relatively even all around us. It was a brilliant first map for sure, but fundamentally flawed by an invisible illusion.
Chapter 2, The Cosmic Measuring Tape. Enter Henrietta Swan Leavitt.
Jumping forward to the early 20th century, at the Harvard College Observatory, Leavitt was doing some incredibly meticulous work focusing on what we call Cepheid variables. Now, these are a very peculiar, completely unique type of star that physically pulsates. They actually grow brighter and dimmer over highly regular periods, like clockwork. By 1908, Leavitt had painstakingly cataloged 1,777 of these fascinating variable stars. And by studying that massive catalog, she noticed a truly profound relationship. The brighter Cepheids pulse more slowly than their fainter counterparts. This became known as Leavitt's law, and let me tell you, it was a real game changer. She essentially created standard candles. Suddenly, astronomers didn't have to just guess how far away a star was based on how faint it looked, because, a dim star could just be a tiny star nearby or a massive one super far away. Now, simply by timing a Cepheid star's pulse, scientists could calculate its exact true brightness and therefore measure distances up to an astonishing 20 million light-years away. She literally revolutionized astronomy overnight.
Leavitt's cosmic measuring tape set the perfect stage for our next great leap. See, before the 1920s, everyone pretty much believed the Milky Way was the entire universe.
Those fuzzy little patches in the sky, like Andromeda, they were just thought to be star systems inside our own galaxy. But then, Edwin Hubble took Leavitt's tool, pointed it at a Cepheid variable star inside Andromeda, and wow, his discovery was earth-shattering. He calculated Andromeda was about 930,000 light-years away, which is far, far beyond the confines of the Milky Way. Even though modern math places it even further, Hubble's calculation instantly shattered the illusion that our galaxy was alone in the universe.
Chapter 3. Finding the True Center. Harlow-Shapley's Deduction.
So astronomers now realize they desperately needed to figure out exactly where we sat inside our newly defined disk. Enter American astronomer Harlow Shapley. Between 1914 and 1918, using the incredibly powerful 60-inch telescope at the Mount Wilson Observatory, he focused all his attention on globular clusters. These things are magnificent. We're talking densely packed groups of hundreds of thousands, sometimes millions of stars, gravitationally bound into a tight spherical shape. They are some of the oldest objects in the universe, dating back over 10 billion years. And they became Shapley's ultimate clue.
Shapley made a brilliant deduction by following 3 simple logical steps. Step 1, he observed that globular clusters tend to arrange themselves in a spherical pattern around a galactic core. Step 2, he realized that from our vantage point on Earth, we don't see these clusters evenly across the sky. Actually, they're mostly visible in one specific direction, towards the Sagittarius and Scorpius constellations. So step 3, the grand conclusion. If the clusters surround the core, and we only see them off to one side, well then the core is over there, and we are emphatically not in it. And this brilliantly illustrates how we finally managed to kick Earth right out of the center of the galaxy.
So yes, Shapley finally displaced us from the center. Now his initial math slightly overshot the distance, but modern astronomy has since refined our actual cosmic address. Turns out we are living way out in the cosmic suburbs. Specifically, our solar system resides in a small partial arm called the Orion Arm, or Orion Spur. We're sandwiched right between the much larger Sagittarius and Perseus arms. And overall, we're sitting approximately 26,000 light-years away from the dense, swirling heart of the Milky Way.
Chapter 4. The Modern 3D Map. The Gaia Mission.
To truly understand the grand design of our spiral home today, we needed a seriously modern tool, the European Space Agency's Gaia spacecraft, which launched back in late 2013. Gaia is essentially a robotic celestial cartographer, and it's mapping approximately 1 billion stars. 1 billion. Yet, here's the crazy part. Charting a billion stars only accounts for a tiny 1% sliver of the Milky Way, which means 99% remains totally unmapped. It truly emphasizes the sheer, staggering vastness of the cosmic sea we're trying to navigate.
But hey, despite mapping only 1%, the data coming back from Gaia is completely unprecedented. It represents a massive leap forward in astrometry, which is just a fancy word for the precise study of the positions and motions of celestial bodies. Now, Gaia might not be a household name quite like the Hubble or James Webb telescopes, but it is silently revolutionizing our understanding. It allows astronomers to trace the arrangement of the spiral arms, study the galactic bulge, and literally watch the dynamics and evolution of the Milky Way as a whole. This precise, comprehensive 3D map is absolutely crucial and will fuel astronomical discoveries for decades to come.
So from believing we were the center of a small sphere to realizing we're just a tiny speck mapping a 1% sliver of a sprawling, magnificent galaxy, our journey of discovery is clearly far from over. In fact, just recently, astronomers analyzing this exact kind of cosmic data found a black hole that suddenly flipped its direction and is now pointing directly at us. No way, right? Which leaves us with one final, deeply provocative question. With all that out there, what other staggering cosmic secrets are just waiting in the dark to be uncovered? Thank you so much for joining me on this explainer. Keep looking up.